Ladies and gentlemen, welcome to one of the last sessions of the ICM2014. Let me introduce Vojtech Rödl. Vojtech Rödl was born in Prague, where he studied at the Charles University. He then visited several institutions at home and abroad before settling in 1988 in Atlanta at Emory University. Rödl is a prominent combinatorist with a broad span of his activity. He was a star solver, or he is a star solver of Erdős problems, and he probably earned the largest amount of his prizes. Well, as we heard from Ben Green a few days ago, maybe until recently. Among many problems which he solved and results which he obtained, let me mention his work on Ramsey theory and particle on packing and covering, solving so-called Erdős-Hánani conjecture, which initiated a new method called Rödl's nibble. Rödl obtained several awards, for example, the Poya Prize in 2012 jointly with Matthias Schacht. Recently as well became honorable professor at Charles University. Rödl was invited speaker at ICM in Kyoto, where he outlined a hypergraph program to the what's now additive combinatorics, or to the question of Erdős-Turan type. Please join me in welcoming Vojtech Rödl.
Thank you. I would like to thank the program committee and organizers for inviting me to give this talk. It's certainly a great honor for me to be here. Thank you also, Jarek, for nice introduction. In the talk, I will discuss some developments in combinatorics which are based. So let's do it this way.
Sir.
Okay, thank you. Is it better? Okay, thank you. In this talk, I will discuss some developments in combinatorics which are based on a technique sometimes called hypergraph regularity method. This method for graphs was pioneered by Endre Semeradi in 70s and 80s. The graph regularity method has been very successful, and many applications in combinatorics, discrete geometry, and theoretical computer science have been discovered. Many variants of Semeradi regularity lemma have been also discovered and have been successfully applied. I will talk about this lemma soon. In this talk, I selected one problem that can be approached with hypergraph regularity method, and will try to outline how it can be solved using that method. I will start with the history of that problem. So perhaps a very distant origin of that, development was in a paper of Schur, who, while investigating a problem in algebra related to Fermat's last theorem, proved the following combinatorial lemma. So the lemma states that if m is an integer and n is bigger than m factorial times e, then for any partition of integers between 1 and n with m colors, or into m classes, which we will refer to as colors, yields one class containing a solution of the equation x plus y equal to z. So here is an example of such a 3 coloring, m is equal to 3, of n equal to 17. 17 is bigger than 3 factorial times e. And here is the solution of the equation, which is monochromatic, x plus y equals to z. Actually, here we would need, I think, only 13 integers, so this is not optimal. Schur became interested in this type of questions, apparently, and he asked whether the similar phenomenon happens also for arithmetic progression. And he, and independently Baudet, conjectured if the following is true. If the natural numbers are split into two classes, then one class contains an arithmetic progression with any given number of terms. And this conjecture was solved by van der Waanden. Here is a finite version of that answer. For all m and k, m will be again number of colors. K is the length of the desired arithmetic progression. There exists an integer n such that any coloring of integers between 1 and n with m colors yields a monochromatic arithmetic progression with k terms. So here we see again an example for k equal to m equal to 3. Then 27 is really the minimum number. Here is one of those 3 colorings, and here is an arithmetic progression in one color class of length 3. So we saw that, for example, Schur and van der Waanden theorems were, as they were established, and one can ask what other results of this type are true. So here so Schur and van der Waanden for arithmetic progression of length 3 we can express as a solution to a linear equation x plus y equal to 2z, where we insist that x is different from y. So natural would be to ask what about x plus y equal to 3z, but it's not a big, it would not take us maybe too long to find the contra-example. There is a 4-coloring of integers, of all set of integers, with no monochromatic solution. So sometimes it's true, sometimes not. And apparently Schur asked that question for which systems of linear equations such a theorem is true. And that was characterized by his student, Richard Rödl, who characterized systems of linear equations. So for, say, arithmetic progression of length 4, we would need 2 equations. So he characterized all systems of linear equations with the partition property for which such a theorem is true. But this is not the direction I will go into, so I just wanted to say it on the side. I will look into some other type of question. So what is the size of the largest subset not containing a solution? So if we ask that for sure, then the answer is very simple. So if we take the integers between 1 and n, then we say that we see that among odd number, there is no solution, right? So there is a subset of density 1/2 with no solution. But on the other hand, if we add just one more integer, that if we have subset of cardinality strictly bigger than upper integer part n over 2, it will contain a solution. So the answer is very simple. That's an exercise. And so natural question arises how it is with van der Waanden theorem. And that question was first considered by Erdős and Turan in 1936, who defined the parameter Rkn, which is the maximum cardinality of a subset of integers containing no arithmetic progression of length k. And they asked if Rkn divided by n is 0, or in other words, if Rkn is little o of n. In other words, their conjecture could be formulated if any subset of integers of positive density contains arbitrarily large arithmetic progressions. One of the hopes while they gave this conjecture was that a positive answer would imply van der Waanden theorem. Why? This is because van der Waanden's proof, which was by double induction, gave only very bad bound, and this would certainly be another approach, and hope would be that this would give a better bound. And indeed, that happened, but a lot later. While Erdős and Turan asked about their question was whether Rkn is small, the first non-trivial result, or first important result, about that parameter was that it is not so small, that their question, if true, is actually very close to it's quite tight. Behren constructed a subset of integers between 1 and n of size n over e to the 0 log n. And for us, it might be enough to remember it's bigger than n to the 1 minus little o 1 for this well. So it's quite close to n. The first results about in the positive directions were given by Ross in 1953. It seems that for k bigger than 3, handling the question is more difficult, and it took still 16 years before Semeradi proved that R for n is little o of n. And finally, in 1975, Semeradi established the conjecture. Since then, different proofs of Semeradi theorem have appeared. But I should say a few words about the Semeradi's proof. It was combinatorial. He introduced some predecessor of regularity lemma, which he proved later, as I will discuss it, and introduced use of quasi-random methods in graph theory. He also used van der Waanden theorem, so his proof didn't give a better bound on RKN, or didn't on the van der Waanden number. Little later, some other proof appeared, so the proof coming from ergodic theory by Fürstenberg and Katz-Nelson. These proofs also don't give any bounds, but were allowed far-reaching generalizations, for example, multidimensional version, which we will see a little later. On the other hand, there is another approach using Fourier analysis, originally started with Ross, and then Sanders and Gowers gave the best numerical bounds known currently. But since I don't have much to say about it, I will not discuss it. I will talk about yet another method, which is using hypergraphs, and this is what this talk will be devoted to. I should also say that several other proofs appeared over the last decade, but I will devote this talk to hypergraph approach. So graphs and hypergraphs, so what they are. So I will start with the definition of a k-uniform hypergraph, or sometimes I will say k-graph, but k-uniform hypergraph. It's a simple thing. It consists of a set of vertices and set of k-element subsets of the vertex set, which is called H set. So the number k will be the uniformity of the hypergraph. So all sets have the same cardinality, k, therefore it's uniform. Here is an example for k equal to 2, so these are the graphs. We will frequently talk about the complete graphs, so here are 2. Complete graph on 3 vertices, complete graph on 4 vertices. Of course, it's trivial, but I just wanted to point out to the notation, the bottom index denotes the number of vertices, top index denotes the uniformity, which for graph, the building blocks are pairs, edges is 2. Of course, there are some other graphs. Here is one nice one. Hypergraph, so here, for k equal to 3, I will try to draw the 3 uniform clique on 4 vertices. So this is harder to draw. So let's draw it one by one. It consists of 4 vertices and 4 to 3 edges. Very trivial, but we will see this picture later. And I would like to make clear that we understand it the same way. So this is the k4-3, obvious thing, 4 vertices, 4 edges. Now, I will start with a definition of the object, which is maybe very particular, but it will have some link to the problem I discussed. So a graph will be called simple triangle graph if each edge is in precisely one triangle. So of course, this is a simple triangle graph. This is a simple triangle graph. Is this a simple triangle graph? Not quite, because that edge is in two triangles. Similarly, this is a simple triangle graph, but this is not, because suddenly adding that last triangle, we got 3 edges contained in 2 triangles each. The big thing with geometrically is a triangle is not a triangle for us because the vertices are not connected, right? So yeah, each edge is in precisely 2 triangles. But if we build the graph this way, then we get a simple triangle graph. In some other context, Brown, Erdős, and Sors in 1973 asked how many edges can simple triangle graph on n vertices have. And that question was answered by Ruzsa and Semeradi 5 years later when they proved that every simple triangle graph on n vertices has little o of n squared edges. And they also observed that their theorem implies Ross' theorem. At least it implies its qualitative version. So it doesn't give n over log log, but it gives R3 and its little o of n. And in some sense, this theorem will be a starting point for our discussion for hypergraphs. So natural thing is how to extend their theorem, if it's possible to extend their theorem to give a result for arbitrary long arithmetic progression. And the one could consider very natural definition is a k-uniform hypergraph would be then a called simple Clique hypergraph if each edge of that hypergraph is in precisely one clique which is one vertex larger than the uniformity. So uniformity is k, the building blocks are of size k, and we insist that every edge is in precisely one clique of the size one vertex larger. And then the question analogous to Brown, Sors, and Erdős would be if every k-uniform simple Clique hypergraph of n vertices has little of n to the k edges. There should have been question mark maybe. We were interested in this question together with Peter Frankl in 90s, early or late 80s and early 90s before he for a while retired from mathematics, and showed that affirmative answer to that question would yield Semeradi theorem. So this question is interesting because it would show a deep theorem. And also, we were able to establish the conjecture or that question for k equal to 3, which implies the Semeradi theorem for arithmetic progressions of length 4. So similarly, as Ruzsa Semeradi proved the result for graphs, and it was giving a result about arithmetic progressions of length 3, this for proof for k equal to 3 gives the result for arithmetic progressions of length 4. And finally, Tim Gowers and my students, Nagel, Schacht, Skokhan, and me, were able to verify that conjecture in general and prove that every k-uniform simple Clique hypergraph on n vertices has little of n to the k edges. And I will refer to it in future as Clique union lemma. So we have such a special object, and it doesn't have many edges. That's the message. So on the next slide, I will show a relation of these simple Clique hypergraphs with the arithmetic progressions. So how they are connected. So in order to establish that connection, suppose that I have a subset of integers that contains no arithmetic progression of length 4, and I have to show that the cardinality of A is little o of n. If I have as my tool this Clique union lemma for 3, I will have to construct a hypergraph, which is 3 uniform, which has constant times n vertices, constant times n squared times cardinality of A edges, and which will be a simple Clique hypergraph, because for those my lemma will apply. And then by Clique union lemma, I will know that the number of edges is little of n cubed, But on the other hand, by construction, it will be constant times n squared times cardinality of A, canceling n squared, we will get that cardinality of A is little of n. So all what we need to do, sorry about this clicking back and forth, is to construct this simple clique hypergraph with that many vertices and that many edges. And this can be done as follows. So the hypergraph will be 3 uniform, but it will be on, its vertex set will be divided into 4 parts. Here they are. They are copies of negative n and n. And the edges, we will add the edges always by the groups of 4, forming a clique. And x, y, z, and w will form a clique if x, y, z, and w satisfy the following. It adds up to 0 and satisfies another equation. 3x plus y minus z minus 3w is 2a. For some a in the set. We are given that set with no arithmetic progression. Well, we have 2 restricting equations. We have kind of 5 variables, x, y, z, w, and a. So we have 3 degrees of freedom. So it's not hard to see that the number of edges is n squared times cardinality of A. That can be proved easily. And by construction, each edge is in at least one clique. We added the edges always to be a part of the clique. But on the other hand, since A contains no arithmetic progression of length 4, one can show that every edge is in at most one clique. That would take half of the slide, but I will not bother you with that. It's a fact, and let's believe it. And therefore, every edge is in precisely one clique, which means that this is a simple clique uniform hypergraph with given number of edges and number of vertices, all what we needed to show to derive that cardinality of A is little of n. So that is the connection. A similar connection can be established in the multidimensional version of Semeradi theorem, which was proved by Fürstenberg and Katz-Nelson. And that says if A is a subset of d-dimensional lattice, which contains no regular k to the d-dimensional sublattice, then cardinality of A is a little of n to the d. So here is the statement for d equal to 2 in contrapositive. Here I have a subset A of 2-dimensional lattice. It's dense, and you see the theorem is true. We found 3 by 3 regular sublattice. Okay, so what I wanted to say that in this case, Solimoschi gave a beautiful geometric construction reducing Fürstenberg and Katz-Nelson theorem from the clique union lemma. So that can be derived as well. So in the next part of the talk, I am going to discuss the method of the proof. And since this is much simpler for graphs than hypergraphs, I will start with graphs and just try to link or say something about what component we will need for the hypergraph. So regularity method for graphs. So what is it? It typically consists from some regularity lemma, either Semeradi or some version of it, and some counting or embedding lemmas. I will show it on examples. And that method is an important tool in graph theory, has had many applications. And what we will do is one of the simplest applications, namely the Ruja-Semeradi theorem. So regularity lemma. So what does it say? It says, informally, roughly, that every large graph can be decomposed, so its vertex set can be decomposed into relatively few, so not many, mostly random-like graphs, bipartite. So this is depicted on the picture by the tubes which have the gray shade, but each of these cubes have the uniformly same gray shade. I will define more precisely what, or absolutely precisely what random-like will mean, but for now, this would be the picture we will be looking at. And there is one thing more on the slide, namely mostly. Unfortunately, it's not true for all pairs of the vertices, so vertex set of these blobs, but it's true mostly. Well, but it's good, at least this much we have. So this is what we can get. So now I owe you what means to be uniformly distributed. So for a graph, if we have two non-empty disjoint sets, A and B, first we will define the density. So for that, we will first say that EAB will be the number of the edges with one endpoint in A and the other in B. Here it's 30, and A and B have each 10 vertices. And then we define the density of the pair AB as the ratio EAB divided by A times B. So in this case, it will be 0.3. So this will be the information we will be walking away from, this information for the next definition. And we will say that pair AB is epsilon regular with density D if no matter which subset A prime of A I will take, A prime is at least epsilon times A, and B prime subset of B, B prime is also sufficiently large, then the density between A prime and B prime doesn't differ too much from the density of the pair AB. So here we see between A prime and B prime, the tone of gray is a little bit darker, so it's a little bit denser, we can think. So, but not too much, just not more than by epsilon. And for another pair, A prime and B prime, it was a little bit sparser, but again, not too much. So it is uniformly, kind of uniformly distributed. In this definition, epsilon has two roles. It sets the threshold for sizes of A prime and B prime. So if A prime is too small, we can't say too much. Similarly about the B prime. And also it measures the uniformity of the edge distribution. So it tells us how far we can go away from the density of the original pair. And with this definition of the regular pair, we now define what it means to have an epsilon regular partition. It will be such a partition where all but epsilon times t choose 2 pairs are epsilon regular. So the number of the red cubes is not too big. And the second condition is just technical. We can have it kind of for free from the proof, so we take it. Namely, we can insist that the sizes of the sets VI are about the same. And with this definition, the regularity lemma says that every large graph admits an epsilon regular partition. So this is the precise statement. We are given epsilon, then we have some upper bound T0 and lower bound N0, I will say. Explain it that every graph which has at least N0 vertices admits an epsilon regular partition where T, the number of the parts, is at least 1 over epsilon, but not bigger than T0. So the reason for this setup is that number of uncontrolled pairs, uncontrolled edges, the ones which are not in regular pairs, is small, will be small. So these are in irregular pairs, then we cannot say anything if they are not regular, so right. And we had at most epsilon t choose 2 of them, so therefore there is at most epsilon n squared over 2 irregular pairs of vertices. And similarly, there are at most epsilon n squared over 2 pairs inside the blobs. And that is because T is sufficiently large and the blobs are of the same size. So therefore, the number of uncontrolled edges is at most epsilon n squared. So we had arbitrary graph, and it was, if it was sufficiently large, we could get a control over most of its edges. As I said, another tool of which we will be using is a counting lemma. So what that says. The counting lemma says that if we have 3 disjoint vertex sets, and each pair has density at least d, and is epsilon regular, then the number of triangles with 1 vertex in each of the set is at least what it would be in the corresponding random graph, which is d cubed times cardinality of ABC. And so this is what we usually use in application, maybe not only for triangles, but for our case, this will be enough. And actually, much less will be enough. We will use just a trivial consequence of this counting lemma, in particular, because by easy averaging, one can deduce that in particular, because we had d cubed times ABC of triangles, there is a 1 edge in BC, AC, BC, AB, 1 edge that is contained in 2 triangles. So this situation we will remember if we have 3 dense pairs and the counting lemma applies. Okay, now I promised I will show how this regularity method works. The proof will not be too complicated, so we just, or will be simple, so I will just state it. So Rusha-Semeradis theorem says that for every delta there exists n 0, every sufficiently large graph don't have too many edges, which is simple triangle graph. So every simple triangle graphs which are large don't have many edges. That's it. So the proof will become by combined applications of regularity and counting lemma. I have to choose some constants, but not for too long. I am given delta. I will set some artificial parameter d for density, smaller than delta, and epsilon, again, small enough to satisfy the counting lemma, and then take n0 very large to apply the regularity lemma and counting lemma. And with that, we are starting to prove. So for contradiction, I assume that I have a simple triangle graph which is large and has many edges. So first I observe that if less than 1/3 of the edges are removed, then triangle must remain. Why is that true? Every edge is in precisely 1 triangle, so deleting 1 edge destroys just 1 triangle. And so if we delete less than 1/3 of edges, 1 triangle must remain. So this is the situation. This triangle remains. So this is what we will use. And now the proof is simple. We apply the regularity lemma, remove uncontrolled edges where they are, in irregular pairs. You see, they disappeared. We also removed the edges which are inside the blobs. They disappeared. And also the edges which are in the pairs which are not so sparse. They have density less than d. The shade of gray is light. We remove them, they are gone. But since we chose d and epsilon much smaller than delta, we didn't remove many edges, less than 1/3. What it means, triangle must remain. Here it is. But then we have 3 dense pairs, epsilon regular, counting lemma applies. Actually, it's a conclusion applies. There is an edge sitting in 2 triangles. What it means, we didn't get the simple triangle graph. So, and this is the contradiction with our assumption that we had many edges. So why did I talk about it? So it means that the number of edges must be less than delta n squared. So why did I talk about it? Because I wanted to point out what are the 2 important tools to have if we want to have a generalization of the regularity method for graphs to hypergraphs. We need to have a regularity lemma that would decompose the hypergraph now into some quasi-random parts, And we have to have a counting lemma that would allow us to find the subgraphs in these quasi-random parts. So the first idea sometimes is good. Here it's not, but I will point out to that anyway. So what would be the first idea? So just go do the same thing as for graphs. So for graphs, we considered pairs, A, B, and counted the number of edges with one endpoint in A and one endpoint in B. I could do it for 3 graphs. I could take such a thing like that, same thing. And then I would define the density same way. And then I would define the epsilon regularity, which would mean same thing. No matter which A prime, B prime, and C prime I take, if they are sufficiently large, the density between A or among A, B, C prime is about the same as the density of original pair. And in this case, we could easily prove the regularity lemma. Actually, we could prove it along the argument of the graph's regularity lemma. However, the counting lemma fails to be true. So in particular, what it means, so for example, if I would say now 4 blobs, A, B, C, D, and consider a 4-partite, 3-uniform hypergraph where each triplet of the sets would have density about 1/2, I could construct it in such a way that it would be epsilon regular, yet it wouldn't contain any clique of size 4, which is the necessary thing which I want to have for any application of the regularity lemma. So one has to do something else. So what is it? Contra-examples for counting lemmas suggest that the hyperedge distribution must be uniform over pairs, not only on vertices. So we will define the density of a hypergraph, here 3-uniform hypergraph, one can extend it, with respect to a graph. So if I have a graph, I can look at its triangles. So here is one, here is another, here are all of them. And we drew the planar graph because it's simpler to draw. The real thing is that we have some complicated graph with many triangles. And on the same set, I consider a hypergraph, 3-uniform. And I will compare these graph and hypergraph. So before I was comparing the graph with respect to subset of vertices. Here I compare the hypergraph with respect to subset of pairs. And we will define the density as a ratio where in numerator I have those triplets which are edges of the hypergraph and also triangles of a graph, and I will divide it by triangles of a graph. And of course, if I would divide 0, I set it equal to 0. So that's the thing. So we have a density, and with this concept of density, we can define the regularity. We will insist that no matter which subgraph G prime I take of G, if it has sufficiently many triangles, then the density of H with respect to G will not differ too much from the density of H with respect to G prime. So this will be the epsilon regularity of a hypergraph with respect to a graph. Actually, we will need on the next slide adjusted version of that concept. In this adjusted version, the graph will consist of 3 parts, and we will restrict to triangles with each edge from different GI. So, and with this concept, one can prove the regularity lemma, which has the same structure as the regularity lemma for graphs. So again, given epsilon, I get some upper bound L0, before it was T0, so that every sufficiently large 3-uniform hypergraph admits a partition now of pairs, not of the vertices, into L parts, where L, I have a lower bound for L and upper bound for L, only depending on epsilon, so that the hypergraph is epsilon regular with respect to all but epsilon times L choose 3 graphs, GH, GI, GJ. So this is one condition, and the other condition, which is, you remember before we had a condition that all sets VI are of the same size. So this is some condition similar to it. Let's forget about it, right? But it's a condition simulating that fact that sets VI are of the same size. And this lemma is already much better, but on the other hand, if we want to prove it, the corresponding counting lemma, it's still convenient to regularize these graphs, which we have in the partition with some small delta, to get them regular in the sense of semi-ready regularity lemma, which yields another partition of the vertices. And with such a lemma, and which was the lemma which we proved with Frankel, we got one can prove the corresponding counting lemma. So how it looks for k-uniform hypergraphs, the structure is the same. So this will be a technical slide, but I will be very brief over it. So if I have a k-uniform hypergraph, the auxiliary partition will partition vertices, pairs, triplets, and until k-1 tuples. And pairs will be behaving randomly, quasi-randomly, or uniformly, I could say, with respect to the partition classes of vertices by the regularity lemma for graph. Triplets with respect to pairs. All the classes of triplets will be regular with respect to pairs. All the classes of k-1 subsets will be regular with respect to partition classes of k-2 sets. But the main thing that the hypergraph will be, the edges of it will be uniformly distributed with respect to the partition classes of k-1 sets. So this is just to say how the structure of that lemma says one shouldn't, I don't force you to get more of it, more from it than that. Anyway, but somehow with this lemma, with such a lemma, one can then prove the corresponding counting lemma, which again, similarly as the triangle counting lemma, in these regular blocks, find some subgraphs, and then one can prove with such a lemma, this Clique union lemma, that every k-uniform simple Clique hypergraph on n vertices has little of n to the k edges. It seems that any proof of the first statement gives us a proof of the second statement, which is stronger, at least as far as we know. So, and which has been now called removal lemma. So the stronger statement, so while the first statement we always restricted to some special class of weird hypergraphs, simple Clique hypergraphs, the second statement is true for all k-uniform hypergraphs. But it's a little bit more complicated, so therefore I started with the simpler statement. It states that for every epsilon and k, there exists C and n0, so that every sufficiently large k-uniform hypergraph satisfies one of the two conditions. Either it can be easily made kk plus 1 free, so I can remove few edges and destroy all cliques of size k plus 1, which we may refer to in future as H is epsilon close to being kk plus 1 free, or it contains many copies of that clique of size kk plus 1. So this is the removal lemma, and this is the statement I will from now on talk for a while about. Well, kk plus 1 is hard to pronounce. I should have kk plus 1 or whatever. So one natural thing is whether one can generalize it, and one can indeed very simple way, or along the proof for the Clique, one can prove it for any k-uniform hypergraph, and one can show such a statement. Maybe simpler way what we can take from it, and this is why it is called removal lemma, is the following. if H contains only a few copies of F, then one can remove few edges from H to obtain a F-free hypergraph. This looks like, or this is a very natural statement, but surprisingly, it has these arithmetic connections. Okay, so this is the removal lemma. So if we have few copies of some hypergraph F, then we can brush off few edges and get completely F-free hypergraph. So this is the version of this removal lemma stated for one hypergraph F. A natural thing, or I don't know, yeah, maybe natural thing is to ask how it would be if we instead of one, have more of them. So would such a lemma be true? So the question is, can F, single F, be replaced by possibly infinite family script F, which either is so that any sufficiently large hypergraph is either epsilon close to not containing any F from F. So what it means, I said it in a clumsy way, I can take a few edges and there is no F in script F, or H contains many copies of some F in script F. So this is the question I will discuss in a couple of next minutes. And actually, so generalizations of the removal lemma. So actually, first time this question was asked, perhaps, was by Paul Erdős, who asked many questions in this area of combinatorics. And actually, he submitted a paper to a conference which we edited with Jarek, the volume. So I am an owner of that manuscript, and here is his writing of that paper, and here is that conjecture. It's his conjecture from 1983, where he asked whether for every epsilon there exists C that depends only on epsilon, and L that depends only on epsilon, so that every sufficiently large graph satisfies one of the two possibilities. Either G is epsilon close to being 3-chromatic. What it means, I can delete just few edges and I get a 3-chromatic graph. So here it's structure of such a graph. We could delete just a few edges. You see, we did. And the graph, we could split the vertex set into 3 classes, each of which was independent set, which means in graph theory that the graph is 3-chromatic. We could color the vertices by independent sets by 3 colors. So either this is true for any graph, and if this is not true, then G must contain many copies of some 4-chromatic graph, which is small. Why small? L depends just on the epsilon. So it doesn't depend on the graph, doesn't depend on its number of vertices. So this was the Erdős question from 1983. Here it is that Gretsch graph, which is in fact not 3-chromatic, right? It's 4-chromatic. So I should mention that this conjecture is precisely what we would understand as removal lemma for infinite family, and it would be a removal lemma for infinite family consisting of all 4-chromatic graphs. Also, I should mention that this conjecture was made in response to an earlier result of Bolobás, Erdős, Simonovic, and Szemerédi, who solved that problem for when 3 and 4 is replaced by 2 and 3, so for the family F3 consisting of all 3-chromatic graphs. And the general form of the conjecture for NER was confirmed jointly. We confirmed it jointly with Duke in 1985. Anyway, but much more is true. In 2005, Noga Alon and Asaf Shapira proved that such a statement is true for any family F. Let's read just the short version of it. which says that if a graph is epsilon far from being F3, that means I cannot remove just very few edges to make it F3, which means that it doesn't contain any member of the script F, then G must contain many copies of some small member from the family F. So the only reason why I cannot make easily the graph F3 is that it will contain many copies of some small member of F. So this is the a short version. So of course, as I already said, for a special case, this is our earlier result with Duke. This proof is based on an iterated application of the regularity lemma. Alternative proof was given by Lovas and Szegedy using the graph limits. And partly motivated by the proof by Lovas and Szegedy, we gave a proof with Matthias Schacht for hypergraphs, which is still something to do because hypergraph regularity lemma is more complicated object and it needed some work. And I should also say that further refinements were obtained by Austin and Thu. These results have application in theoretical computer science in the area of property testing. And in the next few slides, I will briefly say how. So I will now talk about the application of this statement. Sorry, I'm going back and forth. So we should remember that if G is epsilon far from being F3, implies that G contains many copies of some small f in script F. So this is what we should work with from this slide. So many problems discussed in theoretical computer science can be described as follows. So here, this potato, this ellipsoid, represents for us the class of all graphs. And many problems can be described in terms of some forbidden subgraphs. So this will be the green area. And for many natural families F, the problem of decision problem, whether the given hypergraph or graph H is in the family, is computationally hard problem. So for example, if we take a family F4 of all 4 chromatic graphs, as we discussed on the previous paragraphs, the F3 class will be precisely those which are 3 chromatic. And this is well known to be a hard NP, it is known to be an NP-complete problem. So it's a classical NP-complete problem, whether the given hypergraph, or sorry, graph is 3-colorable. So this is denoted, so this hardness in the mind was denoted by this wiggly red line, so separating from the rest. Similarly, one can show that for many natural families, the problem deciding whether the graph is in the epsilon far from F is a hard problem. So what the infinite removal lemma now says, it tells us that there is a simple separating line between the two classes. Namely, the class of those which are epsilon far from being F3 is contained in the class of hypergraphs that contain many copies of some small f. And because it's small, it's simple to decide. In polynomial time, we can just search over all small subgraphs. And because it contains many, we can do even better. One can construct randomized algorithms which distinguish between the membership in the class H, whether hypergraph or graph is F3, or whether hypergraph is epsilon far from being F3. Of course, in the middle nowhere land, we can make errors, but somehow that would be too much to ask to really solve the big problem, right? But it can separate these two classes. And I should say that this type of problem is studied in the area of theoretical computer science, which is called property testing. So I think I have still a couple of minutes, so I will finish with an open problem. So regularity lemma is, or this regularity method, as I said, for graphs and even for the hypergraphs, could have been applied to many problems, diverse problems, and have been successful. Nevertheless, it has, there is a price for it. And the price for it is that it doesn't give good bounds. And so there is some effort within the combinatorics wherever one could prove the statement first with the regularity, try to find some other proof which can get rid of it. Sometimes we are successful, sometimes not, because we chase for numerical parameters, we are interested in them. And one where it was only partly successful is the Ruja-Semeredi theorem. And so I will go back to it and say what it says. So recall, we already saw it many times. For every delta, there exists a zero, so that any simple triangle graph, this is a simple object. Every edge is in precisely one triangle, very particular object, doesn't contain many edges. And we could define Ruja-Semeredi number to be the smallest and zero for which satisfies the theorem. So what do we know about it? The lower bound for this function follows from the construction of Behrend. So one can take the construction of Behrend and construct a lower bound which is of this form. But the upper bound, which I would follow from the proof I just gave you, would not be quite close. So it is this big. So the gaps are pretty large. And so polynomially large tower. And there are a couple of proofs which differ by details, but all of them use quasi-randomness. And in some or other way, one ingenious new approach, but which still uses quasi-randomness in some sense, was invented by Jacob Fox, who recently reduced the tower to C times just logarithm of what we had before, but it's still quite far apart to be absolutely satisfied. So the question might be, improve these bounds, right? And if we should conjecture, maybe, the tower prove that the tower is, height of the tower is independent of delta. Whether or not it's true, I don't know. But let me conjecture it today. Thank you very much. That's all. Thank you.
Thank you very much, Vojta, for a great talk. I don't think this hall is somehow suitable for some fruitful discussion, so I would like to postpone the discussion to the couloirs and to the break in between. Let us thank Vojta again.
Thank you.